This is how I programmed a simple game engine where your character is a ball and you get to move around a planet that gravity attracts you to. As you can see, the camera follows your orientation wherever you are on the planet, and you can customize the angle you view your character and the direction it goes. You can even zoom in and zoom out. Pretty simple, or is it? This idea always fascinated me since building such project always seemed a little complicated. In this video, I'll try my best to explain the mathematics used behind building such a game. This is how I made this game. Before we begin, we need to start by explaining a few mathematical terms that we'll be using throughout this video. First of all, I should show the editor I used to build this. As some of you may have noticed, I am using the Roblox editor to build this game, since I already had familiarity with the language and applying mathematical methods are easy with this engine. We should start with C-frames, or coordinate frames. A C-frame is nothing but a location in the 3D plane, along with a 3x3 matrix of numbers that represent three different directions. This direction over here represents the look vector. Remember, a vector is just a direction with an x-coordinate, a y-coordinate, and a z-coordinate. And this direction is represent where the camera or the character is looking. This one is representing the direction that is pointing upwards, and likewise this one is pointing to the right of our camera or our character. Here's a graphical example. If my character was at 0, 0, 0 on this plane, my character, his face would be pointing to the right hand side, let's say. That would be its look vector. Upwards would be its up vector. That would be represented by the blue arrow. So for example, if something was at the top of his head and it was pointing upwards, that would be that blue arrow. And if there's something was on the right hand side, that would be facing the right vector. Let's get into why C-frames are useful though. Let's take this point A, which is 0.5, 0.6, and 0.7. Things with C-frames is, and bases in general is, we can describe any point, let's say A, with some unique linear combination of these three directions. For example, if we have this elementary basis, which is depicted right here, we have our first vector, which is our look vector, which is 1, 0, 0. Our up vector would be 1 in the y direction, so that would be upwards. And let's say our right vector is 1 in the z direction. We would be able to describe this vector, which is a, by a certain number of each of our elementary bases. The most useful fact about the C-frame is we can convert normal directions in the 3D plane and translate them to different coordinates and different bases. What can be written in terms of one basis or C-frame can also be written in terms of other bases. So for example, if our character is placed here, right now its position is just a bunch of numbers. And likewise with its look, its up, and its right vector. But given A, which is the same as defined as last slide, we can find B, which is the same point A, except translated into our new C-frame or basis. This point becomes useful in the next step of building our game. Understanding on why C-frames and change of bases could be useful when building this project by making movement. First, we're going to define our movement vectors. We are going to use a unit circle with the x and z coordinates to depict how our character is moving forward, backwards, left, and right. We're also going to use the WASD as the controller for the player's movement. For example, if the player is holding the W key, we'll register the direction vector as a unit vector in the z direction. So the z direction would be positive for W and negative for S, for example. If the player is holding W and D keys, we translate that in our code as a unit vector with the same number for X and Z, which turns out to be 1 over root 2, 0, 1 over root 2. Remember, we don't have any Y components for any of our direction vectors since we're not going to be going upwards quite yet. Now that we have our direction vectors in terms of the elementary basis, how can we translate that to our character's movement? First, we need to change the basis from our elementary basis to our character C-frame. As you can see here, we can imagine this to be our character. We can imagine this vector down here to be our direction vector that we have created in our code. No matter how this is rotated or moved around, we'll be able to translate our direction vector and to give it to our character in an appropriate way so we'll know where to move. In conclusion, to get the character direction, we have to get the direction vector based on WASD inputs. We have to translate to current character C-frame, and then what we're going to do in the game is set the ball's angular velocity to that direction. Great, now we know how to move our character. Now, the character can move around the globe with gravity that we've applied to it. But the problem is as the player moves, the character's C-frame has to change as well. Let's see how we need to change our character's C-frame after every movement. Assume we have our character, and the vectors we're working with are already translated to the elementary basis for ease. In this picture, that would mean that our player would be looking in the direction of the red arrow, the top of its view would be in the green arrow's direction, and its right vector would be pointing in this blue arrow. As stated before, our up vector has been normalized to 0, 1, 0, or 1 unit in the y direction. Finding our new up vector is easy because all we have to do is find the difference of our player's position in the globe's position. Or rather, if we call our new up vector n would be the unit of the player position minus the globe position, and that would give us this arrow right here. There we go, we have our new up vector in terms of the elementary basis. Finding the look vector and how it's changed, that's going to be a little bit more tricky. Here's a view of our character more accurate to what the camera might look like in the game. Our character here is moving to the right and forward a little bit. This non-shaded one would represent where we were, and this one is where we're going. And we don't know how this would change the look vector. What do we want to do with the camera? Since we are assuming no rotation in the mouse right now, we only want to see changes of the look vector by moving forwards. In other words, we only care about how far forward the ball goes so that we know how far to tilt the camera downwards in this case. To do that, first we want to find how forward on the globe our character has moved. We're going to get our up vector n, which usually was pointing right here, and we're going to flatten it to the x and y plane by subtracting its z component, and then making it a unit vector again. Now this circle represents the forward and backward movement of our character's original position before this movement here. So if it was going this way, that means it would be going forward only, and this way it would be going backwards. And you could see our new forward vector, which we're going to call v, is a little bit forward on this circle. Now that we have a little bit of an idea of what we're doing, let's find the angle between our normal up vector and the change in x direction, which we call v. To do this, we can use the cosine similarity, which states that when we have two vectors in the 3D plane, we can find the angle between them, or rather, the cosine of the angle between them, theta, by taking their dot product and dividing by both of their magnitudes. In our case, we have our up vector to be 0, 1, 0, and v to plug into this equation. And remember, our cos is just the inverse cos. And we're going to call our new angle between these two a. But remember in this case that both of these vectors that we're using are units already, so their magnitudes are already 1. And now, since we're multiplying by 0, 1, 0, its x and z components are being multiplied by 0, so all we need is the y component of v in our arc cos to find a. Now let's look from the right side of our model. And our angle we'll find is called a. That's what we need to rotate our current look vector, or this red one, by. So we want to rotate our look vector by a degrees to match the rotation of our character. But how do we rotate such a vector in such a manner? The answer is rotation matrices. By substituting the angle that we want to rotate for theta, which that's going to be A, and choosing which axis to rotate around, which will be Z, we can multiply our vector by one of these matrices and get the rotated version of it. So let's see how this applies. So we wanted to rotate our look vector 1, 0, 0 by the angle A around the Z-axis. And this is what that would look like. The angle, or this vector right here, is what this look vector was, and it's rotated by the same angle that was calculated by the distance between these. And that's how I would find our new look vector. But that's assuming no rotation from the mouse. But what if we wanted to rotate it some more to apply a change in the mouse's direction? Now we can do that again by applying another rotation matrix around the y-axis. Let's call B our angle that would get from the mouse by some sort of delta from the mouse in the x direction. Let's see what it looks like now. So as you can see, it's the same angle rotated downwards by our look vector, but now it's being rotated by some angle B, which that's what's changing in this picture, to show a rotation around the y-axis. That's going to be the final version of our new look vector in terms of the elementary basis. But the only question is what's left? We need to translate back our newfound vectors to the C-frame of our character and replace that C-frame using the new vectors found. And that's it. Now we have a C-frame that's updating with the player's movement. Let's get into the last step of building our game, which is placing the camera. Suppose we are viewing our character from its right side, where we have its up and look vector constantly being updated depending on its movement. We need to find a place to put the camera where our player will be looking at the character. Let's start by defining a couple of terms. Firstly, theta. We're going to let this be the angle of the camera, and this is going to be controlled by the mouse change in the y direction. Secondly, it's going to be capital D. This is going to be the distance from the player, which this will be controlled by the mouse scroll wheel. And this is what theta and D will look like. So what about the sides of these triangles? Well, we know from basic calculus that this side is going to be D times cos theta, and this side on the left side over here is going to be T times sine theta. So whenever D or theta changes, both of these values are going to be changing. When D is changing, let's see the camera is zooming out, it'll stay on this line, but be going outwards because it'll both be changing this value and this value. So let's see how we can use these values. Firstly, to go backwards, we're going to start at the position of our character, and we have to subtract d times cos theta, number of the look vector of the character's position. This is why it's useful to use look and up vectors that are units, so it can be accurate in terms of distance when we're multiplying it by some number. Then we need to raise our position by d times cos theta, our up vector, to raise the position upwards. This allows us to fully customize our camera depending on our mouse and scroll wheel. Now, the last step would be setting the camera facing where our character is, but that's the easy part. These two values and controls for the player allows us to fully customize our camera. Let's get into the next steps of building our game. So for the next steps of our project, which I'm going to add soon, or maybe in another video, is going to be add jumping based on the up vector. This will probably be controlled by the space bar, and this will add a force upwards according to the player's up vector. I also want to make transitions between planets. The player will be able to move between planet and planet, and the gravity will reflect what planet the current planet is for the character. And lastly, I want to make a game out of it. I've only built the very structure of the game, but it would be cool to make something like that. And we've reached the end of our video. So I want to thank you for watching. You can play this game on Roblox. So thank you very much all watching. Leave your critiques in the and positive messages hopefully in the uh, comments below, and that'll be it for today. See you in the next one.